All right, so in this last example, we're going to continue on with the same directions as the previous example. And first thing we're going to do is identify the parent function. The parent function would just be f of x is equal to natural log of x. Okay, so describe the transformation. Now this one, you don't really have to factor anything inside the argument because this guy right here is less than 0, right? You know that it's a reflection over the x. Right, your a value is less than 0. Okay, and 2 units to the left, right, because it's x minus -2, and then 1 unit down. Okay, so let's analyze the vertical asymptote by setting the argument equal to 0. X is going to equal to -2. And while you're at it, right, you can state the domain. You set the argument greater than 0. X is greater than -2. All right, so now let's get the x-intercept, right? When you solve for the x-intercept, you're going to have to solve a log equation. And the way you solve the log equation is you have to get this log right here by itself. Okay, so if I move the 1 over, right, and divide by -1, my log will now be by itself. Okay, so I'm just going to use way 1, right? In the previous video, I showed you there's 2 ways you can go use inverse properties, and then way 2, you can just directly convert to exponential form. So just good practice, out of good practice, I'm going to exponentiate both sides by base e. Okay, so I'll show an extra line right here. Both sides by base e. All right, so when you exponentiate both sides by base e, right, this is going to cancel out using your inverse properties. And if you get x by itself, right, 1 over e minus 2, this would be the exact value of your x-intercept, which I will ask on a exam. And the approximate value is when you enter on your calculator -1.632. This is the approximate, right? This is what you will get if you go to Desmos. But, you know, in order for me to ensure that you understand, you know, how do you solve the log equation, right? I ask that you give me the exact value. All right, so there's one last thing, right? We need to plug in a smart point, right? And would you agree that ln of 1, right, would be a smart point, right? Sorry, if I can make the argument somehow equal to 1, and you evaluate this, right? This is saying e raised to what power gives you 1. Well, e to the 0 will give you 1, right? So this will give you 0. So I need to make this argument into a 1, right? And the way you do that is you set x plus 2 is equal to 1, x is equal to 1 minus 2, which is -1. So if you plug in -1, that would be a smart point to evaluate. Okay, so let's plug in -1 into our g function. So g of -1 is equal to negative ln of -1 plus 2, right, minus 1. And you don't need a calculator to evaluate this because you have negative of ln of positive 1 minus 1. And we already know what ln of 1 is, right? E to the what raised to raised to what power gives you 1, and that's 0. So -0 minus 1, no such thing as -0, right? It's just -1. Okay, so you have, you know, -1 comma -1, you have -1.632, right, comma 0. 2 points I would say is sufficient for you to graph. Okay, so if you were to graph this, draw a few tick marks. We said our our vertical asymptote was x is equal to -2. And we have 2 points, right? -1.63, I don't know, maybe somewhere over here, comma 0, -1, -1, somewhere over here. And the graph's going to look something like this. It's going to approach the vertical but never cross it. And again, just from transformation, right, you know that if this is, how do I graph f of x is equal to ln of x? Or y is equal to ln of x? Ln of x will look something like this. And we said it's reflected across the x-axis, right? So if you were to reflect this across the x-axis, right, it would look something like this. And so that's how I know that the graph's going to approach and curve like this, okay, in case you're wondering. You could always do a big picture in your head before you get down to the details and plot points